Now, in our last lecture, we talked about, very briefly, Green's theorem, which said that if we had q sub x minus p sub y in the double integral, then this was equal to the line integral on the boundary. Now, this is a very important theorem. We will deal with it quite a lot, quite soon. But for the time being, we ask the question, as you remember, that when q sub x minus p sub y was 0. Because if it were 0, namely, let us recall that by Green's theorem, very roughly, we had, this was the double integral of q sub x minus p sub y. Okay, here R is the region bounded by C. Okay, C is a closed curve. Now, this told us that if we had this equality, then, okay, the right side would be 0, so the integral would be 0 for all closed nice curves. So there was a significance in this q sub x being equal to p sub y. Okay, when does this hold? Okay. By observation directly. Okay. If Rf, that is PQ, is the gradient of some function, okay. Well, phi here is a scalar valued function. Okay. And okay, PQ have continuous partials, then q sub x is p sub y, because q sub x, let me start with p sub y. Okay, doesn't matter. P sub y is the derivative of p with respect to y, but p is already a derivative. So this is the derivative with respect to y, okay, of p, which happens to be phi sub x. So it is phi xy. Similarly, q sub x is the derivative with respect to x of q, which happens to be phi sub y, so it is phi yx, and these are equal because the partials of p and q are continuous. Okay, this was one of the results we had. Well, so, conclusion. Okay. If f, that is PQ, is the gradient of phi for some phi, okay, then q sub x is p sub y. So this phenomenon that f is the gradient of something is very important. Okay, we will come to this and its physical meaning in detail. Okay, so then we will consider this case, okay, in detail. But now, some more physics. Now, why do we refer to physics all the time? Well, historically, the multiple integration in all its forms, double, triple, or line integrals, they are developed because of the needs in physics in the 17th and 18th centuries in general. So the physical meaning is quite important here. For that, we will start with some physical terminology. Well, first of all, what is a field? What is a scalar or vector field? These are just physical names, terminology for such functions in mathematics. Well, so definition. Okay. Any function, say f from R2 or R3 into R, okay, is called a scalar field. Okay. In mathematics, it's just a function. And any function from R2 into R2, respectively R3 into R3, okay, is called a vector field. Okay. These are just physical terminology. Okay. Mathematically, they're all functions as we know them. Okay. Some examples, some physical examples. Okay. Now, T, X, Y, Z, showing the temperature, okay, at the point X, Y, Z, say on Earth, okay, is a scalar field. Okay. Or, okay, the density function, okay, for, okay, any solid is a scalar field. So if you give it a physical meaning, you obtain lots of scalar fields. Well, vector fields are more interesting because, okay, in many cases, we have a direction assigned to forces, velocity, and all the rest. Okay, in electronics, in magnetics, in electromagnetics, in mechanics, in celestial mechanics, and in hydraulics, in many, many areas, you all have that. Well, let us consider the gravitational attraction. Okay, due to a large point mass M. Well, we all recall that this is a force, okay, which is a constant times the mass it's attracting and the distance between them squared. Of course, this gravitational attraction is a force, it pulls, okay? And at the same time, it has a direction. It pulls it towards itself. So, okay, giving directions, okay, and putting M at 0, 0, 0. Okay. Clearly, this force acts on the smaller mass n, and the bigness, the magnitude of the force is proportional to m as well, to small m as well. But when we want to define, okay, a force in general at all points, irrespective of the point we put there, we usually put a unit mass there so that we don't worry about this m, the small m. Okay. And taking m equal to 1, okay, we get the force at any point x, y, z in space. So the picture looks like this. This is the point x, y, z. And you have a large mass here at the origin. And of course, if you put an m equal to 1 mass there, it will pull it, okay, towards the center. Of course, it's proportional to 1 over r squared, which means that if r is large, this force is small. So we show it by arrows which are getting bigger and bigger. Okay. So this force will be the constant g times 1 times m divided by r squared. Now, r is the distance squared. So it is x, y, z squared. But of course, it has a direction. Okay, this being the magnitude of this force, if we multiply it with the unit vector, it will be the vector force as it is. So what's the direction here? If this is P and this is O, the direction is here. It's in the direction of PO. From P towards O. Thus, okay, it becomes x, y, z. Well, this is O minus P, so it is minus x, y, z. However, this is not unit, so we make it a unit by dividing with x, y, z. Okay. So now, this is the gravitational field, as it is called in physics, which, in a shorter way of writing, is minus gm. These are constants, so not that important for us. We have x, y, z divided by, okay. Now this is the cube of the length. Well, what is the length? The length is x squared, y squared, and z squared. Okay. Square root. Taking the cube, we end up with this function. Now this is of course a vector valued function. The first component is minus gmx divided by this, and so on, and so on. So this is the so-called gravitational field. Due to a point mass, capital M there. Now, likewise, you can talk about I will not go into details. Similarly, okay, for electrical field due to, okay, a charge, a large one, Q, well, this can be negative or positive. So I will take it a positive charge, Q. Okay. Okay, is the following. Well, of course, by Coulomb's law, it's the same as this one, exactly. Okay. But this time, okay, what do we put instead of small m equal to 1 here? Well, we put, by convention, a positive charge, a unit positive charge. So, if Q is 1 unit, I'm not working with units now, you can put all the units in the constant, okay, is a positive charge, then E, the electrical field, will be exactly the same, but now, because at Q we have a positive charge, it will push it away, which means that the direction will be OP in this case. So it will be directly, okay, some constant, okay, well, I'm not worried about those, Q times XYZ divided by the cube root. So this would be our electric field. So it is a vector field. So these are vector fields. Now, in these pictures and the physics we know, if you put a body here in gravitational attraction, of course it will move towards the center directly. Okay? Because we assume it's stationary, we put unit 1 mass there, and it will fall towards the origin. Or in the electric field case, it will go directly away from the origin, okay, in the direction of the spherical row, if you want. It will try to go away. Okay. Now, if the field is more complicated, it doesn't have that physical meaning. How does the mass m move? Okay. When the field affects it. We will not consider a very complicated example here, but because such examples involve what is called partial differential equations, and we are not in a position to solve such things, except in a very simple case, which I will give as an example. Okay. So, as a definition, okay, well, the curve, okay, a unit put at x, y, z will follow under, okay, a field F. Here we take this field always as a force, okay, which acts on it, okay, is called, well, the formal name, an integral curve or a trajectory or a force field. You have lots of names. Is called a trajectory or field line. Okay. Now, how can we find it? Well, an example will serve the purpose. It's a simple one. So let F be a planar vector field, okay, given by x to y. Okay. Find the field lines. Well, let us try to understand what all this means. In the xy system, it says the following. Well, say, okay, on the line y equal to x. Okay. We put a point somewhere. What happens? If x is equal to y, then f xy becomes x1, 2. Because x is equal to y, you take x out. Well, for this positive x, and depending on x, it will be in the direction of 1, 2. Which means, of course, that it will be something like this. Okay, 1, 2. But if x gets larger, this force acting on it will be larger. Okay. And if x is smaller, it will be smaller. On the other hand, if x is negative, of course, you will have the opposite case. Now, suppose you have such a curve, which is f xy. Well, here y is, say, x over 2, just trials. This would be, okay, x 1, 1/2 now. 1, 1, so. Okay? Because you have 2y, y is x over 2, so it's in this direction. In other words, on this line, okay, it will move like this, parallel to y equal to x. Okay. Well, now you must have got the following feeling. If I put, okay, some point here, it will move in this direction, but when it gets nearer to this curve, it will change its direction like this. Because these are, after all, tangent vectors. Because F pushes it, okay, in that direction, and so these will be tangent directions. Similarly here, okay, you will have the opposites, so they will move somewhat like this, and so on. You can continue with the other quadrants just to understand what's happening. Now, how can we find the equation of this trajectory or of these trajectories? Well, this is a very simple observation. In other words, okay, say, okay, x of t, y of t is a trajectory, which means that the point we put at the point x of t, y of t will move according to this scheme as t increases. And we are talking physics, so t is time. Okay. Then, of course, okay, when a body moves on this trajectory, on this curve, x of t, y of t, of course, always you have a tangent vector to it in the direction of motion. And F causes this motion, So F pushes it in that tangential direction. Then, since movement is because of F, okay, the velocity vector is parallel to F. Okay, because F forces the body move on this curve. That means always it moves on the tangent vector direction, and it changes its direction so that its course is on the curve. Well, this says the following. X prime t, y prime t must be a multiple of x of t, y of t, 2y of t, which is f. That's right. Now, this gives us two equations. Okay. It says that x prime t divided by x of t is lambda, which is at the same time y prime t divided by 2y of t. Now, forgetting t's, we can look at it as, okay, or not forgetting them, okay, because we have the derivative divided by the function itself, and they are equal for every t, okay, we can integrate. So integrating, okay, we get logarithm of x of t is equal to, I'm bypassing this lambda, I'm not interested in lambda, okay, I have 1/2 logarithm of y of t plus a constant because we are integrating indefinitely. Well, this tells us that, okay, x must be equal to, at any time t, okay, identify these, of course, take exponentials, that is e to the c times, okay, y of t square root. Okay. So if you want, okay, y is e to the minus c x squared. Now here c can be positive, negative, it doesn't matter. So this expression, okay, can change from 0 to infinity all the time. Now, another thing, because we had absolute values here, okay, this, of course, means that we have here positive or negative values. That is important. So if we have a negative value, we can have here plus, minus all the time. So in short, these are, okay, parabolas of the form y is some constant times x squared. So it says the following. It always passes through the origin. Okay. So it looks like this. Okay. But C1 can change, so it will be like that eventually. Or if C1 is negative, you have the opposites. Okay. It tells us that if you put somebody here, it will move in this direction, or if you put it here, it will move in this direction. So these are the paths your point mass, or whatever you put there, okay, follows. It's interesting to see what happens when x is 0. Well, obviously, you get from the very original function f, okay, if x is 0, you have the vector 0, 2y, okay, which is the j vector, basically. Okay, so it moves here directly up, and here it's the opposite direction. So these are the field lines for f xy equal to x2y. Okay. Well, this method of finding field lines, of course, is quite complicated if you have, for example, even such a simple thing as instead of x, x plus y. Okay. You can roughly sketch the picture, but obtaining these curves exactly can be problematic even if you have nice functions, because it involves solving differential equations, which is far beyond our scope. But the idea is here, so I will continue with that. Okay. Now the next topic is conservative fields. Well, what is a conservative field? Well, a field, of course, was a function. Well, when we talk about conservative field and so on, we are talking about vector fields in general. So f from R2 into R3, R2, or f from R3 into R3 is called a conservative field if f is the gradient of some function for some pi, okay, from R2 into R, respectively, R3 into R. It must be a scalar valued function, but when you take the derivatives, you end up with a vector over there. So, what does all this mean, of course? It all means the following. Also, okay, say f is p, these are functions. Maybe I should put xy here. Okay. qxy. Okay. This, if this is conservative, of course, it is gradient phi. So it is phi sub x, phi sub y. Okay. If this is true, then okay, p dx plus q dy becomes phi x dx plus phi y dy. Well, this is a differential. So, okay, we assume the differential exists. Okay, this is a differential for phi function. Okay, assuming, of course, partials are continuous. So, differential exists. And it's called an exact differential. Well, this is just a terminology in differential equations because there is no partial differential, I mean, part differential or exactly or approximate differential. There can be lots of such approximative definitions, but for us, it just means differential. Okay. As I said, it's a differential. But the formal name is exact differential. Okay. Well, what happens if we have an exact differential? Well, we have various things here. Why is it called a conservative field in the first place? Okay. To explain these things, let us consider a few remarks. Okay, let F, which is PQ, okay, it need not be two-dimensional. You can always define these things for three-variable functions. Okay, let this be a conservative field. Okay. Which means that P is phi sub x for some phi, and Q is phi sub y for the same phi. Okay. Then, okay, the integral of P dx plus Q dy, okay, would be, let us write everything in place and say C is x of t, y of t, and t changed from A to B. So this becomes A to B, okay, P, which was Q sub x, that is Q1, or if you want just x, xy, okay, dx, plus phi sub y, xy, dy. But because we change it to t's, dx now becomes x prime t dt, and dy becomes y prime t dt, and we integrate from A to B. But now, okay, by total differential formula, okay, I'm using all these concepts, okay, because I assume P and Q are very nice. Okay, that is, P and Q, say, have actually continuities enough here, because partials of phi are continuous. So phi is differentiable, so I can use total differential formula. So here, PQ continues. Right. Now it means the following. Now consider this total thing. Okay, forget dt's. You have phi 1, x prime, plus phi 2, y prime. But that's directly the derivative of phi of x of t, y of t, and dt at the end. Well, the fundamental theorem of calculus says that if you take the derivative of a scalar valued function and then integrate it, it's just phi of x of b, y of b, minus phi of x of a, y of a. Well, recall that phi was the potential function. I don't remember if I named it. Probably not. So I should in conservative fields. In the definition, that phi is called, well, let me say, phi is called a potential function. Okay? So this is the change in phi. This is the change in potential function. On the other hand, we know the following, okay? We already know that if F is force, okay, then the integral F dot n ds over C, which is in this case P dx plus Q dy, is work. And it's equal to delta kinetic energy. We, found this in our previous examples. So what's the point? Well, we get delta Ek is delta U, this is the potential. So the change in kinetic energy is the same as the change in potential energy. Okay. Now, if we are considering the standard force of, say, a gravitational force or an electric force, usually these, if you increase your T, okay, they change in the negative direction. That's to say, okay, as a body falls towards, say, a center where you have a large mass, okay, its velocity increases, but its potential energy decreases. Therefore, usually one uses not phi, but minus phi. Just a definition. So, since in many cases in physics, okay, as gravitational or electrical, etc., fields, okay, change in phi, okay, under the force F is negative, namely potential decreases. Okay, one uses minus phi instead of phi. So one gets delta Ek is minus delta phi, or delta Ek, let me use U because that's my potential energy, plus delta U is 0. Now, what's the meaning of this physically? Well, the change in kinetic energy, that is gain in kinetic energy, plus the loss in potential energy is always 0. In other words, the total energy that's Ek plus U, okay, remains constant. That is, energy is conserved. Hence the name conservative field. Basically, it conserves energy. Okay, examples. Well, first of all, let us consider the gravitational energy. or gravitational force. Okay, we figured it out to be xyz. Okay. That was gm. Okay. And okay, let me write it in separate formulation. Minus x over x squared, y squared, z squared, 3/2. Okay. Minus y over 3/2, and minus z over 3/2. So this was the gravitational force, or field, if you want. Well, force is not that correct. We should say field. Because force changes proportionally to the mass, small mass m, that is attracted. But field is the one which applies to mass, small mass equal to 1. So it doesn't change. Therefore, it's better to use this wording. Now, is this indeed, okay, is this, right, indeed a conservative field or not? We can figure that out, okay, quite simply by observation. Now, this is a conservative field. Because, okay, now look at the first term. It's x over the squares of x, y, z added and then raised to the power 3/2. Well, if that's the derivative with respect to x, we should integrate it with respect to x. Okay. What do we get if we do this? Okay. You can check quite easily that what you get is exactly, okay, the derivative of 1 over x squared, y squared, z squared, okay, under the root. Now, what's this derivative? Okay. This derivative would be minus 1/2 of x squared, y squared, z squared, 3/2 times 2x, which is exactly the first component there. And similarly, d by dy of the same thing is minus y over this thing. And similarly, d by dz of this function is minus z over 3/2. You can get this even by observation. Okay, so F is gradient phi. Okay. So the electric field or the gravitational field due to a point mass is indeed conservative. Okay. There are many other examples of this sort, but there are also many examples which are not of this sort. But here, one important thing emerges. That's to say, given a field, even if we know it's conservative, how do we find its potential or its a potential for it, because it's not unique? Okay. In general, how do we find a potential phi, okay, once we know? Don't ask where. Suppose somebody tells us, okay, we know, okay, F is conservative. Okay, there are many ways of doing this. Theoretically, we will show one in the proof, but it's not practical at all. Well, the answer is usually, okay, by direct calculation. Okay. Now some examples for this. Well, let me just go over two examples. Given that f is, okay, an exact differential or just conservative, okay, find the potential. For it. A f x y is given as x plus y squared and 2xy. Okay. Now, how do we proceed? Well, let us check what is given in the first place. Namely, this is our p function. This is our q function. And we know, okay, that phi sub x is pxy, which is x plus y squared, and phi sub y is qxy, which is 2xy. Now, we can start from any of them. Okay, say we start from phi sub x is x plus y squared. Now, how do we get phi from here? Well, let's differentiate it. So we integrate. So integrate partially, i.e. y is constant. Because, okay, this is obtained by keeping y constant. So, okay, we differentiate it with respect to x only. So when we integrate to find phi, we should integrate with respect to x only. So phi xy would be partial integral of this. So it would be x squared over 2 plus y squared x. Okay, when you integrate, because y is constant. Okay, but we have a constant, of course. Now, if this constant contained an y in it, for example, if c was y cubed, when we differentiate with respect to x, we wouldn't see it here, because its derivative would be 0 with respect to x. So this c may not be an ordinary constant, but it can be a function of y. So this can be a function of y, but not of x. Because if we had x in it, when you differentiate with respect to x, we would see it here, but we don't. So it can be a function of y. So write this c of y. Okay. If it's a function of y, differentiating would give this. Well, now let us differentiate phi, since we know it now, with respect to y. This, of course, remembering here, q phi with respect to y is 2xy. Namely, it's q, so it is 2xy. On the other hand, from what we found, we can differentiate this one, which is, of course, with respect to y. So that would be 2xy plus c prime y when you differentiate. X is constant because it's a partial derivative. And compare. Okay. Comparison tells us that c prime y is 0. So c is a genuine constant. That means just a number. Okay, it doesn't have any y's in it because its derivative with respect to y is 0, so there are no y's in it. And we can now put everything together and obtain phi. So phi xy happens to be, okay, from what we have there, x squared over 2, 2xy plus c. If you differentiate this with respect to x and then with respect to y, of course, you get p and q up there. Okay. So this also says that, in particular, potentials are not unique. They change with constants. You can add infinitely many constants. So there are infinitely many potentials. That's why one does not talk about an absolute value, a fixed value of a potential, but rather a potential change, namely delta phi. Now, that, of course, makes this constant unimportant. They will cancel each other. Okay. Potentials are not unique. There are infinitely many of them. As a second example, okay, let us consider a three-variable function. This will be a little bit longer, of course. Given that f, that is PQR, is x plus yz, and xz plus y, and xy plus z. Okay. Now it's given that this is an exact differential, that is, it's conservative. So we want to find phi. Well, this is our P, Q, and R. So P happens to be phi sub x. And phi sub y is Q, and phi sub z is R. This is x plus yz. This is xz plus y, and this is xy plus z. Okay, it's not important where you start. Okay, but say this time we start with, say, phi y is xz plus y. So, again, partially integrating, with respect to y, that means x and z are constants. Okay. We get phi xyz is the integral with respect to y. So it is x, y, z plus y squared over 2. And we have a constant. Okay. But now, because x and z are kept constants, this constant may depend on xz. But there can be no y in it, because its derivative will be seen up there. Now we can continue with the other ones. Well, phi sub x was x plus yz, okay, because it's p. But at the same time, this is from what is found. This is, okay, the derivative of phi with respect to x. So that would be yz plus 0 plus derivative of c with respect to x. Now, note that here z is constant and y is constant because it's partial derivative with respect to x. Okay, so we evaluate, but here this still will be a partial derivative because there is a z somewhere in it, possibly. Now compare. When we compare them, okay, we have yz's the same, so this must be x. Well, this tells me something. Well, c is a function of x and z, and if its partial derivative with respect to x is x, then integrating, that's partial integrating, okay, we have x squared over 2 is c xy, but of course, because we integrated, we have here plus some other c, well, let me say c1, and c1 certainly, because we had a z in here, it can depend on z still. Finally, phi sub z, okay, this was xy plus z, okay, and again from what is found, well, what did we find? We take the derivative with respect to z of phi. Phi was xyz plus y squared over 2 plus dxz, but wait a minute, this should be z, of course, because we integrate this one. Cxz is x squared over 2 plus d1 of z. And this tells me, with respect to z, I have xy plus 0 plus 0 plus derivative of c1. Now, comparing these two, I have xy here and xy here, and c1 prime z must be z by comparison. Now this tells me now that c1 of z must be z squared over 2 plus some d. Now this is just a number. So in total, phi xyz becomes, okay, starting from the very start, it's xyz plus y squared over 2 plus cxz. Now cxz was x squared over 2 plus c1z, but c1z is z squared over 2 plus d. So this is the wanted potential.